In this video, we introduce the concept of activity and we see how it can be used to describe real solutions. Alright, our work so far with chemical potentials has been one in which we've been able to write the chemical potentials for ideal gas or ideal solutions or the solute in an ideal dilute solution. All of the expressions have very similar forms, right? Where simply you have the chemical potential of the species of interest is just the chemical potential of a reference plus a correction from the fact that the conditions that you're interested in, you might be at concentrations different than the reference, right? So your concentration or your partial pressure might be larger or smaller than the reference, and that should change the chemical potential. This is really what that expression tells you. Right, so something that we could actually do is instead of having just this piecemeal type of expressions for each of the cases, just to have a universal expression that then we can apply to the various cases, right? So that's something that we can do right away. Notice that we can say is that the chemical potential of J, or whatever this is, right, or a liquid or a gas, is simply going to be equal to the chemical potential of J at some reference concentration, which could be the standard state or could be the pure liquid, plus RT natural log plus here a measure of the concentration, right? Notice that in a gas that would be the ratio of the partial pressure over the standard pressure. In an ideal solution that would be the mole fraction. Here you have more concentrations, but those are all measures of concentrations, right? So we can use here a measure of concentration that we're going to call the activity. And this activity for now is just an effective measure of concentration. And again, this works always, right? So the general case, the universal case will be this. This is how do you write the chemical potential for any substance under any conditions. Right? And again, that's very useful. Then the only thing that you have to do is say, well, how does this A sub J and that standard state unfold for the various cases, right? So suppose that, for example, you have a gas, right? Well, so if this is the gas, then the activity simply can be replaced by the ratio of the partial pressure of that component over the pressure of the standard state, and the standard state is simply 1 bar. If you have here an ideal solution, well, then this is simply the activity of J, and then the standard state, the reference state, this is going to be simply the pure liquid. And when you have here your solute and ideal dilute solution, then this simply is going to be equal to the ratio of the concentration of that solute over the standard molar concentration of 1 molar, and this reference state is going to be that of a molar concentration equal to 1 molar. And again, this means that the same thing. Okay, so again, notice how we're simply going to have this universal expression, and then you're just simply going to map it into whatever you want using a table like this. Okay, so that is very useful for now. And again, the activity for now is just simply an effective measure of concentration. Okay, so fair enough. Now, in this video, we also want to handle what happens when you're not in one of these 3 cases, right? So notice that this only works if you have an ideal gas or an ideal solution in which both components follow Raoult's law, or the solid and ideal dilute solution in which the solid follows Henry's law. There's actually a range of concentrations here in which none of these conditions apply, right? If you take a look at this one, right, we have that ideal dilute solution would be maybe from here to high concentrations, and maybe from here to lower concentrations of A, but in the middle you have that we don't have a way to actually figure out how to write those chemical potentials, which is most of the concentration range, right? And the same thing will happen with the negative deviation. So that's what we call a real solution, where you don't have any useful law whatever that can capture that behavior, right? So the question is, how do we handle then that case, those real solutions which take place under most concentration conditions, right? Well, so that's something where activities also come in handy, right? So the way that we actually handle this is quite simple. We simply are going to say that in those cases, for real solutions, the activity of a component J is simply going to be related to the measure of concentration that you're interested in, which I'm going to choose arbitrarily to be the small fraction, right? But multiplied by something that is going to be called an activity coefficient. Okay, so this is the activity, and this is called the activity coefficient. Alright, so then what's going to happen here is that this activity coefficient is going to tell you, is going to measure how far away from ideality you are. As a matter of fact, if this activity coefficient is 1, then you are in the ideal case, right? So suppose that now you're interested in an ideal solution, right? In an ideal solution where Raoult's law is satisfied, then what happens is that the activity is going to be equal to the mole fraction, okay? And that means that that activity coefficient is 1. But of course, if you're here, let's take this black line right there, right? Notice that your pressure is actually higher than predicted by Raoult's law. What actually that means is that this activity coefficient will actually not be 1, it will be larger than 1. And in this particular case, what you actually have is that the pressure that you get is lower than that predicted by Raoult's law. So what that would mean is that this activity coefficient is not 1, you're not following an ideal law, instead it's going to be different than 1, in this case it will be lower than 1, and that shows you how far away from ideality you are. In the problems that you're going to do to gain some learning about these activity coefficients, what is going to happen is that you're going to have to recast some of the laws that we have seen, like Raoult's law and Henry's law potentially and so forth, using now activities, right? So let me spend a couple of minutes telling you how that would work, right? So you suppose that you have a problem on Raoult's law, right, in which the ideal case would be something like this. P of A would be equal to X of A, P of A when pure. Right, but now you would like to apply this to a situation where you don't have adherence to Raoult's law. Again, it would be any one of these lines when they depart from the dashed line, which is Raoult's law. Well, the way that you actually do this is fairly simple. The only thing that you do is say, well, for a real solution, this will be the ideal case, and this is the real case. You're simply going to replace that measure of concentration, A, by the activity, which is an effective measure of concentration, but then the law is going to be as it was, right? So no changes whatever. Now the only difference here is that this activity now is going to be your activity coefficient A multiplied by that mole fraction, right? So notice that any deviation of this activity coefficient from 1 will signal that you're not in the ideal case, that you might be in the real case. But if this activity coefficient happens to be 1, then you actually are in the ideal case, right? So again, we get to see once more how these activities serve also as a place-holding expression for almost anything that we want to do with these chemical potentials, Henry's law, Raoult's law, and so forth, right? We can use that just as a stand-in measure of concentration that then we can map into something that we can measure really in the laboratory. Okay, so all right, so let's wrap up this video here. We've done a couple of things in this video. The first thing that we've done is just come up with a universal expression for how to write the chemical potential of any component in any phase in a mixture, and that is extremely useful. For that, we've used the concept of activity, which is an effective measure of concentration. Now, we've also seen that that activity can also be used to try to study deviations from ideality, right? So real solutions in which none of the ideal gas or Raoult's law or Henry's laws work. In that case, then what you have is that the activity can be related to the effective measure of concentration that best characterizes that component that you're interested in, but the difference between them is going to be an activity coefficient, which is simply a measure for how away from ideality you are. Right? In the next video, we're actually going to move away from chemical potentials or their derivation. We're actually going to see how they can be applied to learn useful things about mixtures.